So how do you design an experiment? All right, the first thing that you're going to have to do is, what is this problem that you're faced with? What do you have to solve that is going to require this experiment? All right, so first you have to define the problem. So let's take a look. Here's the problem we're faced with. In this problem, we have a castle, and our engineering team has told us that our defenses are impenetrable as long as our weapon of mass destruction, our catapult, can accurately deliver projectiles to the kill zone to take care of all of these nasty folks that are going to try to attack our castle. So that's what we're faced with. We have a weapon of mass destruction, our catapult, and we need to accurately land projectiles in this area. We don't want to be short, we don't want to be long, we're not trying to maximize the difference, we're really trying to hit a target. So let's see if we can come up with a way to do that by designing an experiment. So let's go back to our experimental design steps. Alright, so we know what the problem is. Right? Set the objectives to achieve for some measurable performance metric. Well, the objective that we have is we've got to be able to consistently land in the kill zone. So there's some distance here that we have, probably a plus or minus about that distance. We have a range that if we can hit that distance consistently within that range, then we will have met the objectives. All right, so that's what we have to do. The next is to brainstorm the product or the process variables, so we can think about what are the factors, okay, or the variables that potentially could be adjusted or changed. So if we take a look at our catapult, we can adjust a lot of things on the catapult. Let's take some pieces apart here. So we have a catapult. We can adjust the angle that we pull it back at. And to help us with that, we have some different size blocks. So we could pull it back to that distance. We could pull it back a little more. We could pull it back at another distance. And what we've done is we've measured how far these are from the horizontal that we would pull down. So we have some blocks that we could use so we can be consistent when we set our level setting. And we could use a big heavy band. We could use a not so heavy band. We could use multiple bands. And we have some locations where we could attach the bands. We have 3 different locations. We could attach the band. I'll get a different one. We could attach the band here in this middle position and come across, attach it over here, and then we're trying to launch that projectile. Now we're not trying to maximize the distance, we're trying to hit a target. So how far do I pull it back? At what is that pullback distance? Alright. Where should I attach the rubber bands? How many bands should I use? The other thing that I could adjust is how much padding do I have here to stop. So there's a couple of adjustments I can have here. I also have some adjustments associated with where do I put the center pin, alright, that's going to be in my catapult. So I could be longer or I could be shorter, and that may have an adjustment in the distance that I achieve. So the whole point is we're trying to figure out which of these variables, and then initially what variables should we study, what are the things that we could possibly adjust. So I've identified a number of adjustments there in the process, but how about the projectiles? I could shoot a smaller projectile, a larger projectile, a really big projectile. I mean, I want to knock out these bad guys, so maybe this big guy is the one that I want to use to knock those guys out. Alright, so, but if I can consistently land them in that distance that I know is my objective, then I'm going to be able to wipe out, you know, that horde of ruffians that are trying to attack my castle. Alright, so one of the things that we could do is to select the variables and the factors to study, and I may have to use a priority matrix or a QFD to do that, where I can take a look at, here's the performance measures that I'm trying to achieve, my objectives. What are these variables that have a strong relationship with the ability to adjust and control to get to that distance? And I may need to use a matrix to help prioritize. Now, a video that you could watch that would help you to understand how QFD can help you with this, we have a video called QFD for Process Improvement. And that'll show you how to take the process steps in a process, look for the variation contributors, and that will allow you to pick the variables to put into a design experiment. And then, of course, we have to come up with the settings that we want to test for those variables. So we've identified a number of variables: size of the projectile, variables associated with our catapult, and we need to just decide, okay, what are going to be the settings that we're going to be testing. All right, so start off with what are the most number of variables that you can have. I would initially limit myself to 2 level settings per factor. All right, once we've narrowed that down, we can go to more settings per factor. But initially, I want to have a lot of factors in my experiment, but keep it at a reasonable size so that I can narrow the field. So that's what we would call a screening experiment, to reduce the number of variables down to those key variables that are really going to have me hit the target every single time. That's what we want to have. All right. The next thing is think about the physics. Think about the physics. What are the things that may work together, that would have an interaction, would have a combined effect? So, does the pullback angle and the number of rubber bands, could that potentially have a combined effect? All right. Does the pullback angle and where it stops have a combined effect? I don't know. Maybe not. Does the location of the rubber band and the number of bands have a combined effect? It may. So what you want to do is think about the physics of what's going on. You know, the ones that we're always, you know, concerned about in a lot of experiments are time and temperature, and time and pressure, and temperature and pressure. And we know from physics that these things have combined effects and they relate to each other. So when you look at your process, you want to think about what are those things that possibly could interact. And we have to think about them ahead of time if we're going to be using a fractional factorial, which will help us to reduce our experimental space. Now, if we have an unlimited budget and an unlimited amount of time, we can run all possible combinations of all factors, but that would be a huge experiment. And, you know, obviously we could study all the interactions that way, but full factorials are not necessarily the most cost-effective or efficient ways to get at the answer. All right, now, next, where are we at? Aha. Conduct a measurement system analysis. Can we repeatably, reliably, and reproducibly measure the outcome from an experimental condition? All right, so what we need to be able to do very consistently is we've got to get our measurement system out there, and we need to find out, all right, how far did that projectile go? All right, how far did that projectile go? And this other projectile. And what we want to make sure is that our measurement system, the way we do it, the tool we use, is going to give us repeatable and reproducible results. So if we have a problem with the measurement system, I don't care how good your experiment is, if there's unreliable data to do the analysis, then how reliable would we consider the results of the experiment to be? So measurement system analysis is key to having a successful experiment. All right, so the next thing that we've got to do, all right, so we've thought about the factors, we've thought about our measurement system, we've validated it with our MSA. All right, then pick the design, pick the lab. You know, we got a list of factors and level settings. We have an idea of which ones we think may interact. So now we need to pick a design lab. All right, so I just happen to have one here. And a design lab that we could use, and this is, and I know it's an eye test for you on video, but obviously we have courses for this at educatevirtually.com. This is a fractional factorial, a Yates algorithm. And what we give you is not only how to use it, but a understanding of how you can study the combined effects of the interactions and the rules that you can use. So even if you're using some software package, you will be smarter than the software because you're going to know where to place the factors, and you'll know which interactions you can study and which ones that you cannot. All right, because the software packages that are out there will let you study anything that your heart desires, whether you may or may not. So this is a 16-run Yates algorithm, fractional factorial. We can study up to 10 factors and up to 5 combined effects or interactions. Very powerful experiment. We use this one often. Very popular design. It's not too big, it's not too small. You can pack a lot of information into it. Okay, so we picked a design. So then the next thing after you pick the design is, where are you going to assign the factors? So the first thing that we have to do is we take the combined effects, the interactions, where we have two factors we think are going to work together, and we assign those two columns first. And in this particular design, we've given you the ability to choose up to 5 combined effects, one from each of these groups. All right, and we're trying to minimize confounding, and confounding would be when the pattern of pluses and minuses for main effect is the same as the pattern of pluses and minuses for the combined effect of the two factors. And to study that, to generate that plus and minus combination, we actually multiply the two columns together to get the new set of pluses and minuses. All right, so we assign the interactions first. The leftover columns, we assign those to the remaining factors, and then whatever's left over after that is, those become unassigned, and we would then pool those sum of squares and degrees of freedom into the unexplained for when we do our analysis. Okay, so we're not going to talk about the analysis right now, but that's what we would do. All right, so we've assigned the factors. Then the next thing, and this is probably the most important, we've got this thing figured out that we're going to run. All right, so what's this experimental combination? And we got to put the pin here, and we know we got 2 rubber bands on there, and it's going to be connected here, and we're going to use the large projectile, and we're going to pull it back 1 3/4 inches, and we get that all set up. All right, now who's going to go make the measurement? All right, to check how far the projectile landed. All right, how are we going to measure it? What are we going to do to capture and evaluate the data? All right, how are we going to set up all the experimental conditions? Can we set the experimental conditions up? That's always a good thing to go through. You've designed this experiment. Can we actually set the settings? We need to make sure that we can do that. So there's a lot of logistics and planning that go into actually conducting the experiment. We've got to do this 16 times. All right, we've got this 16-run experiment. There's going to be 16 adjustments to our catapult, and that process of launching the projectile, we're going to have to set up each one of these, and we're going to have multiple repetitions of firing the projectile from each of the experimental combinations so that we have repeated data. Now, how much data do you need? Very good question. All right, so if I look at this design, it's a 16-run experimental design. There's 2 level settings per factor. So each variable is at the low setting for 8 experimental runs and at the high setting for 8 experimental runs. All right, so if I want to have 20 to 25 data points per experimental level setting of a factor, if I have 3 repetitions per experimental combination, then I will end up with 3 times 8, or 24 data points per level setting of a factor. Now I know that if I got 20 to 25 data points, I can make a control chart, and that will give me a valid mean and standard deviation. All right, now I have enough ammunition so that I can have confidence in my analysis. All right, so I know how much data I need, 3 data points per experiment run, and I'm using the fact that there are 16 experiment runs and there's 8 combinations, okay, for each level setting. So there's 8 experimental conditions for each level setting of a factor. 3 data points per run gives me plenty of data. So we plan all that. We have that all figured out. We decide who's going to be doing what and where and when. And now we can actually run this experiment, collect our data, and then do the analysis. All right, so that's how you would design an experiment.